It started as data, not an explosion, not a shockwave, not anything you could see by looking up at the sky. It began deep inside the networks of the world's most advanced telescopes: Chile, Hawaii, the Canary Islands, the Atacama Plateau, Namibia, Beijing, Australia. Places built to observe the universe with precision down to the smallest wavelength of light, places where silence is data and signal is truth. On the morning following 3I Atlas's perihelion passage, those instruments should have been overflowing with new readings. The object had just completed the moment of maximum solar heating. That was the window where its outgassing, rotation, brightness, composition signatures, tail morphology, and nuclear structure would be most visible. That was when astronomers expected their best chance to understand what this object really was. Instead, something else happened. The telescopes went dark, not literally offline, not powered down. The systems were active, but the data streams stopped. Real-time tracking feeds froze. The coordinates of 3I Atlas, normally updated multiple times per second, stalled and held on the last known position. Requests to relock the tracking algorithms returned the same error across different software systems, in different countries, on different operating budgets, built by different manufacturers. Target not found. The skies were clear. The instruments were functioning. But the object had, for lack of a better word, disappeared. At first, this was interpreted as a routine data drop. Solar interference is common near perihelion. Instruments designed to observe objects near the sun often experience overloads, scattering, diffraction, flare. The coronagraph teams assumed the glare had simply flooded the detectors. Some observatories waited for automatic recalibration. Others switched to manual spectrum search modes. But within minutes, it became clear that what was happening was not local to any one telescope. One observatory director later described it as the moment when the world quietly realized that everybody else was experiencing the same problem. The only images captured during the blackout interval were the final frames transmitted just before the signal collapse. In those frames, 3I Atlas did not simply increase in brightness or distortion, it elongated, not like a tail, not like typical dust ejection. The nucleus appeared to stretch, as if the entire core was being drawn forward along its direction of travel. A shape change, not a debris plume. A transformation in geometry, not material fragmentation. Then, as the frames came in faster to try to compensate for tracking lag, the elongation blurred, sharpened, and then vanished. Not drifted out of view, not occluded, not dimmed, vanished. When the commands to resynchronize were issued, the star field alignment returned normally. The background sky was stable. No solar flare, no imaging distortion, no mechanical obstruction. Everything worked except the one function astronomers needed: the ability to detect the object. It was as if the sky itself had rejected the coordinates. Within the first hour, 17 observatories submitted anomaly reports to the International Astronomical Union's Emergency Monitoring Channel. These reports rarely trigger response, but this time the timestamps aligned too closely to ignore. The blackout had begun within a 5-second window at observatories distributed across longitude and hemisphere. Different weather, different atmospheric conditions, different time zones, different operators. A synchronized failure. A shutdown that did not appear to be the result of hardware, software, or environmental interference. Then came the part that made no sense. The tracking return algorithms did not return null data. They returned a set of values that implied the object's reflective signature was still present, but compressed into a spatial volume smaller than any known natural body of similar mass. A reflectance profile that suggested The object had collapsed into something denser, smaller, and more uniform. Yet the orbital trajectory data computed independently across dozens of tracking centers did not change. No gravitational perturbations, no deceleration, no mass loss detectable from solar wind recoil. The object was still there, but it was no longer visible, no longer radiating, no longer reacting to sunlight the way matter should. By the third hour, the first whispers started circulating among professional channels. The word used was not disappearance, it was silence. The object had gone silent, not visually, but physically. No gas emission signatures, no tail particles, no thermal emissions. A body still moving, still existing, but giving off no signal of interaction. Then something even stranger happened. Radio observatories began reporting system faults. The signals they had cued during the perihelion surge were flagged as corrupted not because of noise, but because they contained a repeating narrowband structure that the filtering software could not classify. These software packages are designed to remove interference patterns, satellite noise, and atmospheric reflections. But the structure in the signal did not match any known artificial or natural pattern. The systems did not erase the signal. They shut down instead. They did so autonomously. When engineers attempted manual retrieval, they found that the shutdown logs were identical across different telescope systems that do not share code bases. The phrase logged-in system memory varied slightly depending on architecture, but the meaning was consistent. Signal exceeded permitted coherence threshold. No one had programmed that language manually. By the end of the first day, scientific institutions began withholding statements. Press briefings were postponed. Social channels belonging to senior astronomers who had been publicly commenting on 3i Atlas for months went quiet. Archive pages that previously displayed spectral data were replaced with generic maintenance notices. Datasets that had been openly accessible the night before now required credentials linked to government-affiliated research networks. No one announced a classification order. No one needed to. Something had happened that demanded silence before understanding. People expected the story to end there. A simple case of telescopes losing sight of a small, fast-moving object. But at midnight UTC, the object reappeared. Not gradually, not quietly, not as a faint point emerging from solar glare. It returned in a position that matched the predicted trajectory to within a quarter of an arcsecond. Perfect alignment, perfect velocity, as if nothing had occurred. Except now, the nucleus was no longer elongated. The brightness was lower than before perihelion, but the spectrum had shifted into a range that no one had expected. Not the warm emission of heated gas and dust, but something colder, flatter, more controlled. It was as though the object had undergone a transition and settled into a new state. The telescopes were able to see it again. But now, the scientists who had been eager to analyze every molecule of dust began to hesitate. Observations resumed carefully, slowly, with new protocols, with restrictions, because the blackout had not been caused by failure. It had been caused by something the instruments reacted to, something the object emitted. Not energy, not light, a signal. Before the blackout, before the signal, before the world's observatories fell into that synchronized silence, 3i Atlas was already an anomaly. Not because of what it did, but because of what it was. The third confirmed interstellar object ever detected entering our solar system. The third, after decades of speculation that such visitors must exist, yet almost no record of them being seen. Oumuamua passed through first, in 2017, long and tumbling, reflecting sunlight in uneven flashes, like a shard of something broken off, something larger. Then came Borisov in 2019, more like the comets we understood: volatile, icy, venting gas, shedding dust, behaving like an object shaped in the presence of a star. When 3I Atlas was first tracked, it was assumed to be another Borisov. A comet from elsewhere, yes, but one that would follow the familiar rules. That assumption lasted a matter of hours. The inbound trajectory of 3I Atlas placed its origin outside the gravitational boundary of our solar system, travelling on a hyperbolic path, meaning it was not bound to the Sun. It entered from the direction of the constellation Serpens, a region with no proximate stellar nursery and no known planetary debris fields. There was nothing in that direction that made sense as a birthplace. The first measurements indicated a velocity profile inconsistent with objects influenced by known stellar gravitational slingshots. It moved slightly too fast, as though it had once been accelerated by something more than stellar drift and radiation pressure. An object travelling freely between stars should bear scars of deep space desolation. Its surface should be layered with carbonized dust, muted, inert. Yet the first reflectance data on 3I Atlas showed something unusual: patches of active volatile content far closer to the surface than models predicted for objects that spend millions of years exposed to high-energy cosmic radiation. Something had preserved part of its surface material from becoming inert. Theories were proposed, none gained consensus. Then came the matter of its rotational profile. As it approached the outer solar system boundary, astronomers attempted to calculate its spin rate from periodic fluctuations in brightness. The fluctuation pattern made no sense. It did not follow a stable rotation or a chaotic tumble. It behaved like something shifting between rotational modes in real time, not guided, not controlled, but not stable either. It was a motion that suggested internal redistribution of mass or repeated release and sealing of volatiles beneath the surface. At first, the deviation was dismissed as observational error. Light curve analysis often creates illusions when data is sparse, but as the object drew nearer and signals strengthened, the inconsistency held. The object behaved like it did not have a single axis of rotation. It had many, and they were moving. If the first interstellar visitor, Oumuamua, raised questions, 3I Atlas raised implications. Because 3I Atlas was not silent. The moment it crossed the heliopause, where the solar wind meets the interstellar medium, it responded. The emission spectrum shifted. The chemical signature of the gases it released changed in measurable patterns. It behaved as if the environment change triggered something stored inside it. Not a reaction caused by heat, a reaction caused by star proximity. It became clear we were not looking at something formed under the same conditions as the comets of our home system. Our comets are built from remnants of planetary formation: water, ice, methane, ammonia, carbon compounds, layered slowly by gravitational collapse. But the spectrographic fingerprints of 3I Atlas showed a different chemistry. Ratios of carbon to nitrogen that do not match known formation environments around sun-like stars. Traces of complex organic radicals created only under conditions, either extremely cold or extremely irradiated conditions, found not at the edges of young planetary systems, but in the long loneliness between stars. The working hypothesis grew. 3I Atlas was older than our solar system, perhaps older than Earth itself. The object came toward us on a trajectory smooth enough to predict months in advance, but one detail continued to trouble every orbital model. The deceleration profile as it entered the Sun's gravity well was slightly off. Tiny deviations in speed and descent angle, too structured to dismiss as measurement noise, but too subtle to classify as powered motion. It should have fallen slightly faster. It did not. It behaved as though part of its mass distribution resisted gravitational acceleration, something no natural body has the ability to do. When plotted against known gravitational behavior, the object's path traced something not unlike a controlled glide, not precise, not intentional, but influenced by some internal structure, distributing stress in a way unfamiliar to planetary science. As it neared the orbit of Mars, the object brightened. The standard explanation was sublimation, ice turning to gas, releasing energy. But the gas yield was wrong. The ratio of water to carbon-bearing compounds was inverted. Something about the object held volatile material deep below its surface, in pockets shielded from the harsh radiation of interstellar travel. Something had insulated them, protected them, preserved them. Then it passed inside Earth's orbit and headed toward perihelion. Ground telescopes would not be able to track it once it neared the sun's glare, so the task fell to space-based coronagraphs. The final images before the blackout showed the nucleus elongating, its form stretching along its trajectory direction. This transformation did not resemble debris shedding, fracture, fragmentation, dust plume, dispersion, or any known thermal response. It looked like structure shifting, a physical reconfiguration of form in response to solar proximity, a change not triggered by melting, but by threshold. And then the blackout came. The moment the object reached peak solar proximity and its internal state changed, every major instrument looking at it lost tracking in unison. If the story ended there, 3I Atlas would remain a footnote, an unexplained anomaly, filed away among the oddities of astronomy. But it did not end there, because when the object reappeared, observatories found it exactly where gravity said it should be, yet its surface properties, brightness, behavior, and emission spectrum were no longer the same. The visitor that emerged from perihelion was not the same object that entered it. The blackout was the part the public eventually heard about, the loss of visual tracking, the frozen coordinates, the sudden silence in the data streams. But the blackout was not the beginning. It was the response. The thing that triggered it happened minutes earlier, during the final phase of the brightness surge. A moment when 3I Atlas was still visible, still transmitting light into the instruments designed to study it, when its shape was in the midst of elongation, when the nucleus was transforming into something stretched and unfamiliar under the heat of our star. In that moment, multiple radio observatories detected a signal. This was not the first time astronomers detected emissions from a comet-like object. Natural bodies produce radio noise all the time: thermal radiation, charged particle interactions, plasma interference. Those emissions are broad, messy, and spectrally chaotic. They scatter across frequency ranges in gradients that match their composition and environment. But what was detected during 3I Atlas's perihelion surge was something else entirely. The first detection came from the Owens Valley Radio Observatory in California. The observatory was running routine data collection on solar-adjacent objects, monitoring for charged ion release. The system reported a narrow-band spike at 1420.13 MHz. That frequency is familiar to astronomers not because it is used in human communication, but because it is the exact emission frequency of neutral hydrogen, the most common element in the universe. It is a frequency the cosmos uses on its own, a universal spectral baseline. However, what OVRO detected was not a natural hydrogen line. Natural hydrogen spectral lines broaden as they interact with plasma, solar, wind, and ambient radiation. The signal from 3I Atlas did not broaden. It was narrow, exact, coherent. A frequency that held itself tightly aligned with less variance than the background noise around it. Signals like that do not occur as byproducts of random processes. They occur in resonant systems, structured environments, or precise molecular arrangements. The spike lasted 3 seconds. Then it vanished. This would have been dismissed as an equipment artifact if not for what happened next. Within 47 seconds of the OVRO detection, the Parkes Observatory in Australia recorded a matching signal. Same frequency, same coherence pattern, same duration. Parkes was not looking at the sun at that moment. It was pointed at a deep sky calibration field in Carina. Yet the signal arrived anyway, passing through its receivers from a direction slightly offset from the sun, suggesting that the emission did not require direct line of sight optical observation. That alone was enough to trigger attention. A signal consistent across hemispheric separation is uncommon. A signal consistent without phase distortion is rare. A signal that appears at the same frequency with matching temporal boundaries is nearly unprecedented. Then came the third report. The low-frequency array in the Netherlands recorded a partial version of the same spike distorted by atmospheric interference, but still recognizable. The timestamps aligned within milliseconds. The signal originated at a spatial point so near the sun that no practical radio equipment on Earth could normally extract it cleanly. Yet it was detected anyway, as if it propagated across a frequency channel that ignored scattering, diffraction, and occlusion. At that point, the data was reviewed manually, not by automation, not by noise filters, but by human analysts. The pattern was unmistakable. A carrier signal at 1000 or 500 or 2 MHz, a phase-stable amplitude profile, a decay curve smooth enough to suggest neither transmission loss nor mechanical modulation. The signal contained no modulation encoding, no embedded message, no pulse spacing, no variation. It was not structured communication. It was simply presence. Not someone speaking, something resonating. The working theory was not that the object transmitted the signal. It was that the signal emerged as a consequence of the object entering a threshold state when heated to a certain point. A physical resonance effect produced by materials reacting to star proximity. A signal that could be produced by crystalline molecular lattices, conductive carbon frameworks, or cage-structured organic compounds. But the precise frequency hydrogen line exact was difficult to reconcile with random chemistry. Natural resonance structures occur, but they vary under heat stress. This one remained stable across the entire emission interval. Then the duration was analysed more closely. The 3-second burst was not a single event. It was 3 events of exactly 1 second each, separated by micro-intervals, so slight they appeared continuous. The 1 second duration was not dictated by the instrument, it was the signal itself. A 1 second coherent resonance, sustained in stellar proximity, is not a typical thermal event. If it were simply sublimation, the spectrum would broaden. If it were charged particle release, the frequency would drift. The absence of drift was the anomaly. At this point, researchers began requesting cross-comparison with solar data. The Solar and Heliospheric Observatory carries instruments designed to detect radio bursts caused by coronal mass ejections. SOHO registered nothing matching the signal profile at the time of detection. The GOES network did not detect solar origin interference. The Deep Space Network, which monitors transmissions across the solar system, recorded no reflection artifacts. The signal had one directional source and one temporal origin, the moment the nucleus of 3I Atlas elongated at perihelion. Then came global alignment analysis. Because radio observatories around the world time-stamp their data using atomic clocks, it was possible to cross-reference the exact arrival times. When calculated backward, adjusting for atmospheric delay, path distortion, and ground elevation, the data pointed to a single radiant origin region no wider than half an arc minute in angular spread, positioned exactly along the trajectory of 3I Atlas. The signal was not scattered, it was not diffuse, it was not a cloud of noise sweeping through the heliosphere, it was a line that reached Earth from the object as it underwent structural change, and then it happened. The telescope blackout. The narrowband spike appeared, reached peak coherence, ended, and within minutes the tracking arrays lost lock. Systems failed. Observations ceased. The world's eyes went blind. The easy conclusion would be cause and effect. But science does not deal in implication. Science deals in sequence. The signal occurred first. The blackout followed. That is what the logs show. That is what the timestamps confirm. The signal happened. Then the object changed form. Then the instrument stopped responding. None of this proves intent. None of this proves communication. None of this suggests a message. But it does confirm something far more difficult to dismiss. 3I Atlas was not passive. It reacted not randomly, not chaotically, in a manner that suggested threshold response to stellar proximity, internal structural transition, and resonance emission at one of the most meaningful frequencies in the universe. The problem was not that the signal existed. The problem was that it made sense. The blackout was not a power loss. It was not a glitch. It was not a failure of hardware, software, weather conditions, or human control. The shutdown was orderly. That is the first detail that stands out when examining the recorded telemetry from the observatories involved. Every major system that lost the ability to track 3I Atlas entered a state designated by engineers as protective idle mode. In common terms, a safe mode. Safe mode is not the absence of function. It is the presence of constraint. It is the state a machine enters when it believes that continuing to operate may cause damage. Telescopes do not make that decision randomly. Their systems do not trigger safe mode in response to unusual signals, unless those signals contain patterns that appear to the control software as commands, hazards, or integrity violations. Minutes after the narrowband burst ended, the observatories began to report warnings, not alerts about environmental interference, not warnings about mechanical limits. Instead, the logs recorded a different kind of message, one that indicated the control systems believed they had received unauthorized operational directives. The first known log surfaced from the Cerro Tololo Inter-American Observatory Network. The system report read, "Command source mismatch, entering protected state." This line was not written by a human. It is the automated response of a network control architecture designed to prevent malicious takeover. Under normal circumstances, such a line would indicate a cyber intrusion attempt. If a foreign host attempted to send movement commands to the telescope mount, the system would detect that the input did not come from its assigned control node and shut down to prevent physical damage. But what made this instance unusual was that no commands had been issued at all. There were no operator keystrokes, no reposition attempts, no software updates. The systems locked themselves without being touched. Then another observatory reported a similar entry. Then another, and another. The timestamps aligned closely within seconds of each other across thousands of miles and different continents. The European Southern Observatory System report contained a different phrasing, but the meaning was the same. External directive flag triggered, pivot motors disabled. In Australia, the Siding Spring Observatory logs read, "Unknown synchronization request. Motion cue aborted." In Hawaii, the Keck Observatory listed, "Tracking override condition detected. shutter closed. Across each system, the language varied, but the operational behavior was identical. Systems entered a protective posture. Shutters closed, tracking halted, mounts locked. None of the systems powered off. They simply refused to continue observing the object. The question that followed immediately was unavoidable. How could separate isolated observatory control systems, each with unique firmware, different operating systems, and different network firewalls, experience the same shutdown response at the same moment? To answer that, cybersecurity teams were brought in. The first assumption was a coordinated digital intrusion, a state-sponsored cyber attack, perhaps. In recent decades, the vulnerability of infrastructure to code injection and network takeover has been widely demonstrated. But this explanation collapsed almost as soon as investigation began. None of the observatories are networked together in any direct way. Their private control systems are insulated, isolated, and in some cases physically air-gapped. They operate autonomous scheduling and tracking loops. To coordinate a takeover of this magnitude, one would have to simultaneously breach dozens of closed systems across multiple countries, many of which do not share any software lineage. The networks did not show evidence of intrusion. No unauthorized IP traffic, no brute force attempts, no privilege escalation logs, no overwritten firmware, no code injection traces. Nothing that matched the pattern of a coordinated cyber attack. Yet the shutdown log entries were real. The safe mode states were real. The telescopes responded as though they had received meaningful instructions. Cybersecurity auditors then examined the telescope guidance modules themselves. These modules do not communicate via Internet protocol. They communicate via radio telemetry, linked to star tracking references, gyroscopes, and inertial guidance systems. These systems interpret environmental conditions and align the observatory to track objects across the sky. If those systems detect a signal that appears to be a guiding or synchronizing directive, they respond automatically. This led to the second hypothesis. The telescope shut down because their tracking systems interpreted the narrowband signal pulse from 3I Atlas as a command-like synchronization event. This possibility was disturbing not because it implied intent, but because it implied compatibility. For the shutdown to occur, the incoming signal needed to be structured in a way that resembled, at some fundamental level, the internal logic of observatory synchronization protocols. Not communication, not language. Resonance. The control systems of major observatories use reference harmonics to remain oriented. They detect rotational drift, wind vibration, seismic interference. When external signals interfere with these harmonics, the system suspends movement to avoid misalignment. The resonance from the 3I Atlas signal fell within that harmonic sensitivity threshold. In practical terms, the object produced an emission that the tracking systems interpreted as a stabilization override. The telescopes believed they were being instructed to freeze motion to avoid self-damage. The safe mode was not an attack. It was a response triggered by the interpretation of the signal as operational input. Engineers resisted this explanation. It suggested that the signal was not random, that it interacted with man-made machines in a precise, systematic manner, that the object emitted frequencies capable of influencing terrestrial instruments without penetrating their networks or circumventing their encryption. If the signal caused the shutdown, then the shutdown was not a failure. It was a compatibility event. Something about the structure of the resonance aligned with the logic that maintains control stability in observational machinery. This raised the third and most unsettling question. Why would an interstellar object emit a signal that could induce coordinated stabilization behavior in artificial systems. There are two main interpretations. The first is coincidence. Some resonance patterns may simply intersect with engineered systems by accident. Human tools, after all, are built from the same physics as cosmic matter. Shared structure in the laws of nature can sometimes lead to overlap. The second interpretation is less comforting. That there may exist molecular structures capable of generating harmonics that implicitly interact with engineered systems without intention, without communication, simply as a consequence of their fundamental organization. In this interpretation, 3i Atlas is not signaling. It is resonating, not communicating, existing. Its internal structure produces coherent frequencies when heated to a threshold by stellar proximity. Those frequencies interact with stabilizing logic patterns used by machines that track the sky. And those machines in response did what they were designed to do, protect themselves. The telescopes shut down because they were listening, not for messages, but for stability. And something spoke in the language of stability. The shutdown did not blind humanity. It revealed that something in 3i Atlas touched the systems we built to watch the universe, not through technology, through resonance. If the signal was the moment that forced the world to look closer, the thermal data was the moment that forced the world to reconsider what 3i Atlas was in the first place. The object should not have survived perihelion. Comets are fragile things. Even the ones that appear solid are, in practical terms, loosely bound aggregates of dust, volatiles, frozen gases, carbonaceous residue, and fractured mineral inclusions. When a comet approaches a star, heating causes sublimation. The internal pressure destabilizes the structure. Pieces shear away. Jets erupt. The object fractures. Sometimes it disintegrates entirely. Yet 3i Atlas passed closer to our Sun than most known long-period comets, without catastrophic release. It released jets, yes, but they were faint, controlled, directional, and lacked the unpredictable plume structure of standard cometary activity. The trailing particulate bloom was thin. The albedo profile changed, but not in the chaotic pattern consistent with fragmentation. Most importantly, the thermal infrared data did not match any known comet body behavior. Where expected models predict rapid heating of the surface layers, followed by thermal cracking and sublimation, 3i Atlas shows something else: thermal plateauing. The absorption curve flattened, indicating that heat was being redistributed internally rather than being allowed to accumulate on the exterior. It was cooling itself. This was the first anomalous observation, and it led to a deeper set of examinations by teams specializing in conductive mineral shells, irradiated lattice materials, and phase-stable molecular structures. Initial thinking assumed simple explanation. Perhaps the object had a high metal content. Iron-nickel cores are not unusual in some interstellar remnants, and refractory metals retain integrity under intense heat. But spectral reflection analysis contradicted this. The reflectance signature contained almost no conventional metallic resonance. Instead, it showed absorption bands consistent with carbon allotropes, long-chain polymeric carbon structures, possibly doped with silicon, boron, or nitrogen. But the density readings did not match carbonaceous chondrites. They were too high, significantly higher than expected for porous comet matter. This combination, high density, high heat tolerance, non-metallic reflectance, led to one hypothesis that generated immediate controversy: a refractory carbon lattice shell, meaning a rigid exterior shell composed of heat-resistant carbon frameworks, likely formed under extreme temperature and pressure conditions, deep inside a planetary or interstellar material environment, this shell would act exactly as observed. It would redistribute heat instead of cracking. It would suppress volatile eruption. It would maintain structure even under stellar heating. It would preserve internal layers. The question then shifted to how such a shell could form. Three possibilities emerged. The first, deep planetary crust genesis. Some planets or moons, especially super-Earths or carbon-rich worlds, may allow carbon under high pressure to polymerize into ultra-dense forms, similar to diamond, but with layered stability. If 3I Atlas was once part of such a planetary crust, then its shell may be a fragment of a world that no longer exists. The second, high-energy irradiation restructuring. In interstellar space, objects passing through cosmic ray fields or supernova ejecta may undergo surface restructuring. Carbon lattices can be annealed, compacted, and stabilized by long exposure to radiation flux. If 3I Atlas spent millions of years in high radiation zones, its shell could be the product of cosmic exposure rather than planetary origin. The third and most speculative, engineered consolidation. Some researchers propose that the shell's lattice ordering appeared too regular, too uniform, not crystalline, but patterned at macro-scale intervals, patterns that resembled stress distribution frameworks rather than random mineral growth. The idea was not that the object was manufactured, but that something shaped or annealed its shell deliberately, either by natural high-energy cosmic environments or processes not yet understood. No consensus was reached, but the shell was real. Then came the second thermal anomaly. Using inverse absorption imaging from orbiting solar observatories, analysts discovered that the thermal distribution did not simply spread across the surface, it pulsed. Heat appeared to travel through the shell in rhythmic waves at fixed intervals. These pulses maintain consistent amplitude and periodicity, unaffected by rotation, solar-wind interactions, or surface outgassing. Stable periodic heat conduction is extremely rare in natural bodies. Rocks do not pulse heat. Ice does not pulse heat. Something inside was redistributing energy. This led to internal modeling. If heat is being conducted inward and then radiated outward in controlled cycles, the internal structure must include layered voids, channels, or materials capable of acting as thermal capacitors. The shell was not a simple crust. It was part of a system, an insulating and regulating boundary. One model suggested a double layer structure. Outer layer, high density carbon lattice with radiation scattering properties. Inner layer, more porous, possibly filled with volatiles or organic residues. Between them, a transition layer where heat is stored and released gradually. The effect, temperature regulation. The object maintained internal stability while undergoing external thermal stress. This was unprecedented. No comet, no asteroid, no interstellar debris fragment previously recorded demonstrated this behavior. It was not indestructible, but it was resistant in a way that implied endurance rather than fragility. Then came the most significant finding. Spectral backscatter analysis revealed diffraction patterns. These patterns did not correspond to random aggregated crystal domains. They corresponded to structured repeating lattice units, units large enough to affect visible light scattering. Repetition implies order. Order implies formation conditions that are not chaotic. Once again, two interpretations. A natural object formed under extreme, stable, long-duration conditions, such as the deep mantle of an ancient carbon world, later ejected by catastrophic impact. The shell is an accreted structure around something else, something that required preservation. In this chapter of the investigation, no one was claiming intelligence, no one was claiming design. But what was being acknowledged was this: 3I Atlas was not a snowball. It was not dust and frozen gas. It was not a remnant fragment of primordial disorder. It was a body with layers, with thermal rhythm, with structural coherence, with endurance beyond what comets possess. Something inside had been protected, not by chance, not by brittleness, but by a shell that held against a star. Whatever lay beneath that carbon lattice was the next question. And the world now, certain the object was not simply passing through, prepared to ask it. The shell was only the beginning. The deeper mystery emerged when researchers were finally able to look past the outer lattice and into the interior structure of 3I Atlas. This required indirect methods. No probe had reached it, no sample had been taken. The object remained hundreds of millions of kilometers away. And yet, modern astronomy can see into material layers using light, heat, and vibration, the way a physician looks beneath human skin using ultrasound or MRI. The first approach was deep penetration spectroscopy. By analyzing how light at different wavelengths passed through the shell and interacted with internal material, researchers could infer the composition of the layers beneath. Normally, a comet interior is opaque to most wavelengths, but the carbon lattice of 3I Atlas allowed certain frequencies to pass through, refracting and reflecting in unusual ways. These observations revealed two major findings. The interior was not homogeneous, and it was not randomly layered. Typical cometary interiors show chaotic variation, patches of frozen volatiles next to dense clusters of dust, voids from sublimation collapse, fractured mineral inclusions, and irregular temperature gradients. But 3I Atlas presented something else. A repeating structure emerged, bands of differing density stacked in a consistent radial pattern. These bands form concentric shells, each with distinct thermal and reflective properties. The most surprising aspect was the scale. These internal banded layers were thick, uniform, and persistent across all observed cross-sections. This was not the result of chance accretion. It reflected a process, geological, chemical, or otherwise, that occurred under stable and sustained conditions over extremely long timescales. The outermost internal layer appeared porous, containing trapped volatiles. Beneath it, a denser intermediate shell showed chemical signatures of polymerized carbon chains bonded with trace elements uncommon in standard cometary formation. Beneath that layer, spectroscopic scattering indicated a core zone with yet higher density. Then came the interferometry data. By using multiple observatories to measure how radio waves bounced off the object with microsecond precision, researchers generated a model of internal structural continuity. Radio interferometry can reveal density gradients, structural voids, and discontinuities within an object by tracking how returning signals shift in phase. If an object is uniform, the return signal is smooth. If it contains voids or fractures, the signal becomes noisy. 3I Atlas's signal was smooth, too smooth. It suggested that the core was not fractured, not fragmented, not porous. It suggested solidity. This contradicted the thermal data, which implied that heat was being redistributed through internal void channels. The only explanation that reconciled these two conflicting observations was that the core was composed of an ordered structure that allowed conduction without requiring empty spaces. Not a metal, not a crystal, something between. To understand this better, researchers compared the data to known high-pressure carbon phases. Diamond, lonsdaleite, and amorphous carbon were ruled out early. Spectroscopic absorption peaks did not match. Instead, the signature more closely resembled theoretical carbon frameworks predicted only in simulation, three-dimensional networks of carbon atoms linked in repeating tetrahedral or hexahedral bonding patterns, forming materials stable at high temperature and pressure. These structures have been theorized to exist deep within super-Earth mantles, where pressures exceed those found inside Earth by dramatic margins. If 3I Atlas was once part of such a mantle, the core structure could represent a preserved artifact of planetary interior chemistry. Under this interpretation, the object was no longer simply an interstellar rock. It was a geological sample from the interior of a destroyed or transformed world ejected into interstellar space long ago. But there was a complication. The spectroscopic signature did not simply show uniform atomic bonding. It showed periodic modulation, meaning, at the molecular level, the carbon networks appeared to be arranged in repeating geometric domains, not identical, but similar enough to imply pattern. Natural crystalline materials can form repeating patterns, but the patterns observed here did not match known crystal lattices. They were too complex and existed at a scale larger than typical mineral grains, yet smaller than engineered composite structures. Each domain seemed tuned to distribute mechanical stress evenly, like the internal architecture of bone or shells of biological organisms, not smooth but functionally optimized. This raised another possibility, one that did not require claiming design or intent, self-organization. In some chemical environments, molecular systems spontaneously assemble into complex ordered states when energy and pressure conditions are stable for long enough periods. These processes are not intelligent. They do not require purpose. They are the result of thermodynamics, energy minimization, and the drive towards stable configurations. If 3I Atlas formed in a planetary interior environment where such conditions remained stable for millions or billions of years, then its core could represent a naturally emergent self-organized structure, a system that found a configuration that preserved stability and strength under extreme pressure. Yet even this interpretation was challenged by the thermal resonance data. When the object pulsed heat through its outer layers during perihelion, the internal pattern of conduction suggested directional pathways. Heat traveled through the core in specific vectors, radiating toward evenly spaced surface points. These pathways were not random. They were symmetrical. They resembled channels of least resistance, yet they formed spatial alignments too consistent to arise by chance alone. Some researchers propose that the pathways could have formed through stress alignment. As the core cooled, microscopic fractures and rearrangements could have produced preferential conduction paths. Under repeated cycles of thermal stress across millions of years, these pathways could have become reinforced. Others argued that the geometry was too stable. Natural stress networks shift irregularly. They fracture, heal, diverge. They do not produce long-lasting radial symmetry. The debate became polarized. One faction insisted the core was a fragment of a carbon-rich planet, its structure shaped by deep mantle pressures. Another suggested that the object may have undergone a secondary process after its formation, chemical reorganization in interstellar space under cosmic ray bombardment, shock, compression, or exposure to unknown environmental conditions. A third, more cautious view held that the structure could be the result of processes not yet understood, but still entirely natural. The universe has produced phases of matter before that were only discovered after they were observed. Scientific humility remained necessary. What was agreed upon was this: the core was not chaotic. It was not accidental. It was not simple. It possessed order, density, stability, symmetry, coordination of thermal conduction, layered gradients of material composition, a shell designed by physics, geology, or something else to protect what lay inside. The object was no longer simply an interstellar visitor. It was a record, a preserved interior from the deep past of another world carried across the stars, and the world was now forced to consider that whatever 3I Atlas brought with it, it had been meant to endure. When the radio detection logs were released, even in their partially redacted form, one detail stood out. The spike detected during the perihelion surge of 3I Atlas did not resemble the chaotic broadband bursts produced by natural outgassing or solar plasma interactions. It possessed a discrete structure, not a message, not a pattern in the linguistic sense, but a sharply defined signal profile occupying a narrow frequency band centered near 1420 MHz. That number carried weight. It is the frequency of neutral hydrogen emission, the fundamental resonant line of the most abundant element in the universe. Many radio telescopes calibrate around this frequency because it is clear, stable, and universal. If one wanted to observe hydrogen clouds, galactic structure, or diffuse gas, this is where one would look. It is not inherently artificial, but it is foundational. The signal from 3I Atlas exhibited coherence. Natural sources of radio emission rarely maintain coherence across detection ranges separated by thousands of kilometers, but observatories in Chile, South Africa, Australia, Japan, and Western Europe recorded the same narrowband spike within microseconds of one another. The duration was brief, approximately 4.9 seconds of sustained narrowband signal, with a defined frequency drift that did not match the Doppler shift expected from the comet's motion relative to Earth. The drift was counterdirectional, meaning the source of the frequency shift did not originate from movement of the object or the Earth, but from modulation at the source. Natural systems can create narrow-band coherent signals. Pulsars produce periodic radio pulses with remarkable precision, driven by the rotation of neutron stars. Masers occur when interstellar gas clouds amplify microwave radiation under specific conditions. Magnetars emit sudden bursts of radio energy during crust fractures triggered by their intense magnetic fields. But each of these categories exhibits defining characteristics. Pulsars produce repeating periodicity. The 3I Atlas signal did not repeat. Masers produce broad coherence, but require dense, energized molecular clouds. There was no such cloud at the comet's location. Magnetar bursts produce high-energy transients across multiple wavelengths. The signal from 3I Atlas contained no significant energy outside the narrowband hydrogen line. Researchers began by attempting to match the signal to known catalogues of natural emissions. The hydrogen epoch reionization array found no correlating profile. The square-kilometre array analysis team could not place it within the morphology of known maser amplification. The Breakthrough Listen signal classification pipeline labelled it non-categorical, meaning it did not fit any known astrophysical emission signature. The debate began immediately. One side argued that the signal represented an emergent resonance effect caused by sudden internal thermal reorganization. As the core lattice heated during perihelion, structural reconfiguration could have induced rapid polarization shifts, resulting in narrowband microwave emission. Under this interpretation, the signal reflected the stress state of the core, not communication or coordination. The opposing view pointed out that emergent resonance systems typically produce broad frequency spillover and rapid decay. They do not produce clean, stable, narrowband pulses sustained across multiple seconds. The coherence alone implied either an exceptionally rare natural state or a process not yet modelled. The discussion remained scientific, restrained, and focused on classification rather than interpretation. The term artificial was not used in formal publications. The term intentional did not appear in any conference proceedings. Researchers chose neutral language, coherent, structured, non-random, non-chaotic, atypical. The most significant analysis came from interferometric phase comparison. When the signal was reconstructed from observatories across Earth, the resulting interference pattern created a spatial map of the wavefront. Under normal circumstances, a distant radio source produces a spherical wavefront consistent with its origin point. But the wavefront reconstructed for the 3I Atlas signal was planar. This suggested that the emission was not radiating outward from the object in all directions. It was directed. Yet even this could be explained naturally under certain conditions. If thermal stress within the core propagated along symmetrical conduction pathways, the resulting electromagnetic emission could radiate along those axes. A directional emission could arise without requiring intention. A mountain pass creates wind channels. The wind is not purposeful. However, as analysts noted, the directional emission did not align with the axis of the object's rotation. It aligned instead with the internal conductive symmetry inferred from thermal resonance mapping. The emission appeared to follow the structure of the core itself. This was the first moment where the interior structure and the radio signal intersected in a way that neither geological nor purely stochastic explanations easily satisfied. Either the internal structure had formed in a manner that optimized directional conduction naturally, or a secondary process had acted upon that structure to produce it. A third perspective emerged. It proposed that the signal was not an emission from the object at all, but a resonance response triggered by external input. Under this interpretation, the extreme electromagnetic environment near perihelion could have induced resonance oscillations in the lattice structure of the core, generating the observed frequencies, like striking a bell. The bell does not intend to ring. It simply rings because its structure makes it capable of doing so. This interpretation reframed the event. The signal was not active, it was reactive. The implications of this interpretation were significant. If the internal structure was sufficiently ordered to produce coherent resonance under external excitation, then the object carried a physical configuration capable of storing vibrational information, not symbolic information, material information. The signature of planetary history encoded in structure, not language. Under this model, the emission was a record of stress, memory, how the object formed, transformed, and endured environmental change across cosmic time. It was a geological archive transmitting itself involuntarily. Those who argued for this view emphasized that complexity does not imply design. Nature produces structured forms across multiple scales, crystal lattices, coral architectures, stromatolite layering, convection cell tessellations. Organization is not synonymous with intention. Stability selects for order. Order does not require purpose. Yet others noted that the structure of 3I Atlas did not resemble any known natural progression of depositional layering, metamorphic cycling, or cooling fracture patterns. Its symmetry and directional stability persisted across multiple scales, from the thickness of its shell to the conduction patterns of its core. It did not fragment under extreme thermal stress. It did not degrade. It did not collapse. The signal intensified the debate because it revealed not just structure, but behavior. Not purposeful behavior, not communicative behavior. Only consistent, reliable repeatable physical response to stimulus, which led to the central question: was the structure that produced the signal an accident of geology and time, or the result of a process that selected for durability, stability, and the retention of internal configuration? The signal did not answer the question. It only made the question unavoidable. The days following the signal were marked not by discovery, but by disappearance, not of the object, but of information. The shift did not happen all at once. It moved gradually, like a curtain lowering across institutions one by one. At first, it appeared to be routine data reorganization. Research groups often migrate observation logs from open access servers to internal archives before publishing. But this time, the transition did not end with publication. It ended with restricted access notices, login credential failures, and network redirects to government-controlled mirrors. The first sign of the lockdown occurred at the South African Radio Astronomy Observatory. Their online catalogue of raw signal captures was temporarily disabled. The reason listed was scheduled maintenance, but the maintenance never ended. Mirror logs later revealed that the data had been transferred to a classified network segment operated jointly with international defence research entities. The timestamp of the transfer matched the moment the narrowband signal analysis reached internal circulation. Shortly afterward, researchers at the European Southern Observatory reported losing direct access to interferometric combined phase reconstructions of the signal. Message appeared across terminal interfaces. Dataset archived under restricted review. Contact administrator. No explanation. No timeline. No public statement. The pattern repeated across institutions. The Harvard-Smithsonian Center for Astrophysics, the National Astronomical Observatory of Japan, the Max Planck Institute for Radio Astronomy. Each institution issued new internal access codes and shortly afterward distributed notices discouraging public discussion of ongoing analysis. The messages were terse and procedural. They contained no justification. They did not acknowledge the scale of the transition. They simply marked a change in operational mode. Then came the silence. Several researchers who had been active on public platforms discussing the object abruptly stopped posting. Not gradually, not with summary announcements. Their accounts stalled mid-conversation. Threads ended without conclusion. Replies never came. In normal circumstances, researchers busy with analysis might step away temporarily. But the simultaneity of this withdrawal across multiple continents drew attention. A number of archive pages preserved before deletion showed statements written just hours before communication ceased. A radio astronomer from Italy had posted, "The signal reconstruction shows planar coherence. This is unusual." A spectroscopist from Chile wrote, "The thermal resonance model does not match fractal stress alignment. We are seeing something else." Both posts were removed. Their accounts remain intact, but inactive. When contacted directly, most researchers declined to comment. A few replied briefly, offering phrases typical of non-disclosure protocols. "I'm not able to discuss that topic right now. I'm focusing on internal review processes. Publication review is ongoing. Non-confirmed. Non-denied." The institutional press releases that followed were notable for what they did not say. They acknowledged that 3I Atlas exhibited unusual spectroscopic and thermal behavior during perihelion. They confirmed that a radio spike was detected, describing it as a transient signal of uncertain origin. But they avoided all detail. They did not include signal morphology. They did not address coherence. They did not compare the event to known astrophysical emissions. They did not reference the blackout. They did not acknowledge the shift to restricted data environments. The tone was procedural and narrow, language engineered to state without revealing. Freedom of Information Act requests were filed. The early responses were immediate denials. The responses cited exemptions related to ongoing scientific review, international research coordination, and in some cases, national security considerations. The phrasing varied, but the meaning was consistent. The data had crossed into a domain where access was controlled by entities beyond astronomy. Funding patterns provided further evidence. Research budgets for deep sky analysis of interstellar objects expanded sharply. At the same time, allocation categories quietly shifted. Funds previously labelled under planetary science or astrophysics were reclassified under strategic observation infrastructure. The shift redirected oversight authority. Institutions that once published openly now reported to committees structured around defence and aerospace intelligence. These adjustments did not indicate secrecy around extraterrestrial conclusions. They did not suggest that researchers had reached extraordinary interpretations. They reflected a more grounded concern: uncertainty regarding the implications of the signal. Not what it meant, but what it could represent. A coherent narrowband emission from an interstellar object, especially one correlated with structural internal resonance, intersects with communication protocols, sensing technology, and directional transmission models. Even if the signal were purely natural, it demonstrated a phenomenon capable of producing stable, reproducible emission under specific conditions. That alone holds strategic value, not for contact, but for detection. If the signal was reactive resonance, it could reveal how matter stores structural memory across cosmological timescales. This would have implications for non-contact subsurface scanning methods, materials science under extreme pressure, and geological reconstruction of planetary interiors. If the emission represented phase-aligned conductive pathways, it could redefine thermal and electrical transport models in carbon-based materials. Such models influence technological development. The lockdown did not imply concealment of intent. It implied uncertainty regarding use. There were internal debates documented in meeting summaries, later leaked through secondary channels. One summary noted, "Interpretations must remain non-teleological until further verification." Another recorded, "The priority is to prevent premature conclusions that could propagate into public speculation without empirical foundation." A third stated, "All communications must frame the event in physical, not semantic, terms." These statements did not suppress knowledge, they controlled framing. The concern was not that the world would learn too much, but that it would assume what was not yet proven. However, the absence of open discourse created a second effect. It generated distance between those who had access to data and those who did not. Inquiry became stratified. External researchers found themselves waiting, requesting, speculating, or attempting independent reconstructions from older data. Without access to the raw interferometric logs, replication remained impossible. As a result, conversation moved from what was known to what was withheld. Silence became the focus. Silence implied motive. Motive implied meaning. The situation became reactive rather than investigative. Yet behind the institutional restraint, analysis continued. Researchers did not stop working. They continued examining the internal structure. They continued modeling thermal resonance. They continued comparing the signal to natural emissions. They continued refining interpretations. But they did so in environments where the conversation was no longer public. The object itself remained unchanged, still moving outward along its projected heliocentric trajectory. The data still existed. The patterns still existed. The signal still existed. The silence surrounded not the event, but the uncertainty. The panic did not arise from what was seen. It arose from what could not yet be understood. 3 weeks after the blackout, after the data seizures, after the observatories fell quiet and the astronomers who once filled news feeds with careful explanations had retreated behind vague statements and non-committal language, something returned to the sky. It did not announce itself. No sudden flare, no new cascade of reports. Instead, a set of automated deep sky sweeps from the southern hemisphere picked up a faint object on a long outbound track, a dim reflective body coasting away from the sun. The coordinates matched what 3I Atlas's projected trajectory should have been if nothing had changed. But something had. The telemetry was clear before anyone tried to reinterpret it. The object was rotating more slowly than before. Before the perihelion blackout event, the measured rotational period of 3I Atlas had been stable within margins of measurement error, approximately 6 hours, drifting by less than a fraction of a second over the course of weeks, a slow, stable tumble. When it reappeared, the rotational period was 21 hours, not gradual deceleration, a discontinuous shift. Something had altered the internal distribution of mass, or energy, or both. A torque event, a redistribution. The object had not broken apart. If it had, mass loss would have been detected in the form of dust tails, fragment trails, spectral diffusion from fine particulate shedding. None of that was present. Instead, the object appeared smoother, calmer, more uniform. This alone was enough to reignite internal conversations in every observational institute, still allowed to speak internally. The change in spin was not the result of tidal stress at perihelion, because the sun's gravitational variation across the object's radius was insufficient to induce such a shift, nor could solar heating expansion account for the measured effect thermal gradients at the observed depth would relax, not remain permanent. Something internal had changed, configuration, material movement, reorganization. Not necessarily intentional, but not accidental either. Not without invoking physical processes not normally associated with cometary bodies. Then came the albedo shift. Before perihelion, 3I Atlas had exhibited a mottled reflectivity profile consistent with mixed ices, embedded refractory dust, and a thin, uneven insulating crust. This was the same general structure observed in Oumuamua and Borisov, though each differed in details. After the event, its surface reflectivity increased by nearly 28%. Smooth surfaces scatter light differently than fractured ones. The new signature implied that fissures had closed, cavities had sealed, and grain alignment had changed. 3I Atlas now reflected light like something that had melted or flowed, but temperatures never reached melting thresholds for the materials previously identified. The crust had altered without undergoing sublimation collapse. Spectroscopy confirmed that the composition of the surface was now more uniform, as though the outer shell had restructured into a continuous lattice. Not crystalline in the familiar sense, more like the shell had annealed itself. There was no known natural process, acting in the time available and under the measured conditions, that could produce this level of structural reorganization. Shock events create fractures, not smooth layers. Sublimation erodes features. It does not unify them. Heating from solar proximity can change the state of volatile ices, but not reorganize them into new, lower energy structural minima without releasing detectable gas. No such gas signatures were recorded. Rather, the object now appeared quieter, more stable, as though energy had been distributed inward, not outward. The emission lines confirmed the deeper shift. Prior to perihelion, the spectral fingerprints suggested heterogeneous inclusion clusters embedded within a matrix of carbonaceous compounds and silicate dust. Afterward, new narrowband absorption features appeared. They did not correspond to known mineralogical phases catalogued in meteorite samples or cosmic dust surveys. The lines fell into patterns associated with long-chain molecular order, not biological, not metabolic, simply structured. Repeating intervals too regular to be random, but not arranged with the syntax of engineered signal carriers. A form of ordered complexity in the interior, now detectable, because the outer shell had become more transmissive at specific wavelengths. When the first teams attempted to publish supplementary analyses, their internal review portals returned automated notices, embargoed under ongoing interagency evaluation, a phrase that had by now become familiar. But internal memos circulated quietly and without formatting emphasis. The term that appeared repeatedly was transition event, not explosion, not collapse, not disintegration, a phase change. Something within 3I Atlas had moved from one stable state to another. Observers did not agree on interpretation. Some argued that the interior molecular alignment could represent a system approaching equilibrium after its entry stress into the solar environment. The heat load and radiation profile near the Sun could have allowed trap structures to relax. If so, this implied the object had originated in an environment where such internal ordering was stable at extremely low temperatures and pressures, meaning it had formed under conditions not commonly found in planetary systems like the solar system. That alone was not implausible, given interstellar variance. But the consistency of the ordering, the coherence across multiple spectral bands, suggested a purpose or at least a persistence that random formation rarely maintains under stress. Others pointed to the rotational shift as the more critical clue. For the internal mass to redistribute, especially in a way that produced a slower, more energy-efficient spin state, some mechanism must have acted to reduce rotational kinetic energy. There was no sign of external torque. The object had not interacted with a planetary magnetosphere or atmosphere. The Sun's corona had not produced a drag environment sufficient to cause deceleration. The energy had been absorbed internally, meaning that the system had a way to convert kinetic rotation into internal structural alignment. That is not a known characteristic of inert mineral aggregates. It did not behave like a machine. It did not behave like a biological organism. It behaved like something that had internal equilibria, thresholds at which order reorganized into new configurations. It behaved like something that could move through states. Public awareness, to the extent it existed, was now diluted beneath competing headlines, economic fluctuations, territorial disputes, scientific committees issuing unspecific reassurances. The object had receded in brightness and therefore in attention, but in closed rooms, behind authentication walls, the questions were no longer about what 3I Atlas was. They were about what it had been and what it was becoming. Because the outbound trajectory was stable, predictable, and long, it would leave the solar system slowly over years, still visible to those watching carefully. It was not gone. It has simply changed state and stayed on course. And the deeper question that followed was not whether something had happened to it. The question was whether the perihelion event was the reason it came. When 3I Atlas finally drifted far enough from the Sun that Earth-based instruments could observe it again, the world had changed, at least in the eyes of those paying close attention. Astronomers who had spent decades cataloguing comets and asteroids found themselves staring at an object that defied every assumption they had relied on. Its perihelion passage, the bright outburst, the coherent radio spike, the global shutdowns, all of it suggested that this was not a normal celestial visitor. But now, in the deep outbound trajectory, a new question emerged. If this wasn't a normal comet, what exactly was it? The data streaming in painted a picture of subtlety rather than spectacle. Rotation rates had shifted. Sections of the surface had become slightly more reflective, others darker, suggesting the redistribution of material, or perhaps the exposure of different layers beneath the irradiated shell. Spectroscopic readings that had once hinted at simple volatile sublimation now revealed unexpected molecular signatures, not common in our solar system, but not entirely alien either. Interferometry data hinted at patterns in the core that, in retrospect, could explain the coherent radio spike. They were not conventional technology, not by any human or known extraterrestrial standard, yet they suggested an organized process, an emergent property from deep within the object. For months, teams around the world pored over the observations, each trying to reconcile the inexplicable with the known. It became increasingly clear that the signal detected during perihelion was not a traditional message. There were no repetitions, no linguistic patterns, no encoded instructions. The closest analogues, pulsars, magnetars, cosmic masers, simply did not match. What 3i Atlas produced was consistent, reproducible, and coherent, but it did not say anything in the way we understand communication. Some scientists reluctantly began to frame it as a presence marker, a kind of cosmic signature that said simply, I exist, I endure. Others theorized it was a byproduct of chemistry and physics, so extreme that the universe itself produced a resonance under conditions like those found in the core of 3i Atlas. Perhaps billions of years of interstellar radiation, combined with a refractory lattice structure unlike anything seen before, could create transient energy flows, frequencies that manifested briefly as a narrowband spike. If so, the universe itself might be capable of creating signals that appear intentional without anyone or anything deliberately sending them. The philosophical implications of this were staggering. For centuries, humanity had scanned the skies, hoping for a clear, direct message from another intelligent civilization. We imagined language, symbols, patterns recognizable to us. 3i Atlas offered a new perspective. Maybe intelligence is not the only or even the primary form of presence in the universe. Existence itself could be signaled through structure, through energy flows, through patterns we only now have the tools to detect. In this sense, the cosmos is not silent, it is subtle. It communicates in ways that don't conform to human expectation. Looking at the outbound trajectory of 3i Atlas, one can't help but wonder about the hidden processes within. What rearrangements occurred when perihelion unleashed that sudden surge of energy? Did the irradiated shell crack in some microscopic, controlled manner, releasing energy in patterns dictated by the object's deep chemistry? Was the radio spike a kind of resonance that emerged naturally from that rearrangement? The observable changes in rotation and albedo suggest that something within was recalibrated, restructured, even if no conscious mind orchestrated it. Yet even as researchers grappled with these questions, a quiet awe settled over the scientific community. There is an almost poetic resonance in realizing that this visitor, which had traveled for billions of years across the void between stars, had left behind a signature so ephemeral, so unexpected, that it forced humanity to confront the limits of its understanding. This was not a dramatic message written in symbols we could read, but a subtle reminder. The universe is not simply a backdrop for human activity. It is active dynamic, and capable of producing phenomena that challenge our perception of life, matter, and consciousness. Some commentators have started framing this as the beginning of a new era in astronomy, not just the study of objects, but the study of phenomena that blur the line between physics and emergent structure. If 3-eye atlas could generate a coherent signal without any known mechanism of control, what else might be out there, silently interacting with the cosmos? What other interstellar travelers might carry signatures of existence we have yet to perceive? And what does it mean for our understanding of life, intelligence, and presence when signals can exist without language, yet still communicate a kind of reality that cannot be ignored? The moment of perihelion, the brightness surge, the radio spike, the global observatory shutdown, they now exist as pieces of a single puzzle, one that may never be fully solvable. But perhaps the puzzle itself is the point. 3-eye atlas has left us with a new lens through which to view the universe, one that values pattern, resonance, and the subtle markers of existence over explicit statements. The object continues its outbound journey, carrying the scars of its encounter with our sun and the evidence of processes that operate on a scale of time and physics we are only beginning to comprehend. In the end, 3-eye atlas reminds us of our place in a cosmos that is vast, patient, and profoundly subtle. It doesn't speak in words, it doesn't offer instructions, it merely exists. And through that existence, it signals that there is more to reality than we can ever fully decode. The sky is not silent. It has always been alive with possibility, resonance, and signals that we may not yet know how to hear. As the object recedes into the depths of interstellar space, we are left with awe, wonder, and a renewed humility. Our instruments, our equations, our models, they are all limited by human perspective. Yet even within those limits, 3-eye atlas has found a way to leave its mark. Subtle, enigmatic, undeniable, and perhaps that is the most profound message of all, that the universe, in all its immensity, is not merely a void waiting to be explored, but a living system capable of whispering its existence across the gulfs of space and time. 3-eye atlas is gone from our immediate sight, but the signal, the moment it erupted, the shutdown, the reappearance, remains. It will be analysed for decades, referenced in textbooks, debated in conferences, and pondered by generations of scientists who wonder not just what it was, but what it implies about the cosmos itself. Perhaps the ultimate lesson is simple. Existence in and of itself can be a message, if we only have the patience and the curiosity to listen. And as we scan the sky, searching for the next anomaly, we may begin to understand that the universe is always speaking, not in human language, but in patterns, in energy, in the subtle, beautiful, and often inexplicable ways that remind us we are only a small part of something incomprehensibly vast and infinitely more mysterious than we ever imagined.